Thank you, John. Thank you so much. Let me first thank the family. Professor Van Vlack was very special. I'll tell you why in a second. The faculty and the department for this honor. This was the first book. I'm sure you guys recognize this. This is the first book I bought. In India, I was really poor, so I could not even get a Xerox copy. So I had to borrow books from somebody too. So when I came to Berkeley in 1983, this is the first book. It wasn't a new book, it was a used book, but it was okay. But it's a book that I use still because we teach undergraduate material science classes, and this is our Bible. So thank you to the man. What I wanted to do today, we'll talk about the technical stuff tomorrow. What I want to do is to provoke. Berkeley is going through, you guys seem to be quite placid, cool compared to what's going on in Berkeley. It's now very fashionable in Berkeley to have the usual 60s kind of revolution. I'm a pacifist. I believe in Gandhi and stuff. But I want to churn up intellectual stuff. So especially for the students, the young people in the audience, I want to provoke you into thinking about stuff. And energy is going to be the vehicle we're going to use. What I'm going to try to describe to you is my own journey, and I will tell you a little bit. So this talk has two parts to it. The first part is something which John talked about, is SunShot. And it was a government program, and I'm going to describe a little bit of that, what we did, why we did, how we did. And the second part of it is, what did I learn from that as a material scientist, a materials physicist? What did I take away from that? And what are the things that we should be aware of? Okay. Energy is a place mark, a moniker for how we live life. Okay. Well, it impacts us in so many ways, and you will see some examples of that today. It's appropriate that we're actually in a presidential library. I am going to talk about a few presidents, and so you can take a guess as to who it is. How many of you are aware of this program? The Lunar Landing. Yes, 1956-57 was an important point in the evolution of this nation, because Yuri Gagarin and the Soyuz program had just put man into space, not landed on the moon. And so there was an intense amount of activity in the early 60s in this nation. I was just born at that time. And that led to the formation of NASA. And then you all know what happened July 1969, man on the moon and stuff like that. What you don't know is all of the collective effort that went in. A nation got motivated. Not just engineers, not just NASA folks, an entire nation got motivated. Okay. That's something I want you to take away from today's, I hope you will take away from today's lecture. So I start with perhaps my favorite president, John F. Kennedy, and many of you have heard this. We only heard these on crackling radios, you know, those itty-bitty Panasonic radios where you hear all kinds of noise, and you hear this in the background. So I'm going to play for you a couple of videos.
We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard. Because that goal will serve to organize and measure the best of our energies and skills. Because that challenge is one that we're willing to accept, one we are unwilling to postpone, and one we intend to win.
Fast forward 2011, President Obama, he used almost exactly the same kind of language, which said, hey, look, let's bring the best minds of this nation. Bar none, this is the most creative country. Have we lost our way? Perhaps yes. But we should have no doubt that this is the most creative nation on the planet. And so President Obama said, this is early 2011, bring the best minds, State of the Union address. Bring the best minds, the scientists, engineers, folks like ourselves. Ask them to focus on the biggest problems of their lifetime. And he said, we will fund it. And that led to the formation of the SunShot program. And there was a lot of folklore behind the SunShot name. The Moonshot program was the Apollo program. So one of our colleagues, Arun Majumdar, was deeply involved in the formulation of this program, wanted to hark back to the Apollo program. And therefore we said, instead of the moon, forget the moon, we'll go to the sun. And therefore it became the SunShot Initiative. It was funded at a very high level. But I'm going to take you through our thinking process as to how we ran a government program. And typically when you hear a government program, you say, okay, somebody is on free money, et cetera, et cetera. What I'm going to tell you with some examples is you can take taxpayer investment and intensely pursue problems, pursue large problems. And I'm going to give you numbers. So this will be a technical talk without any Hamiltonians, without any physics in it. Okay, tomorrow we'll talk about Hamiltonian. But perhaps, and me, I knew nothing about solar cells. I'm a condensed matter physicist. I look at correlated systems. So my biggest job there, I think I'm really very happy about this, is people. And let me begin with one of the people. She's right here, Rachel Tronstein. Welcome, a future governor of the state of Michigan. And I'm serious. You didn't see me laugh. I'm really serious. Understatement to say that she saved my life at least 20 times. Because I was a university professor going to Washington in a worst possible scenario. I could have been whooped in this job. I had fantastic people. Therefore, I think Rachel will agree, although I think we also figured out there was a lot of fluff in the system. Okay. So I want to make a few points. This is the core team that we put together. Let me tell you loud and clear, we did not grow the bureaucracy. Instead, we shrunk it by 30%. And this lady was actually the first to trigger that. I remember the day that, I will not tell you what exactly she started with, but we ended up reducing the size of the program, federal people and contractors, by 30%. When we started, we had 62 people in our program, 31 federal employees and 31 contractors. By the time the two of us had left, it was 42 people running a $300 million program. And the rule of thumb is approximately you need about $10 million per Fed, and they can manage those programs. That's the first thing, that we actually made the process a lot more efficient. Your tax money was being better utilized, and when you were so cynical that, oh, these government guys don't do anything, well, wrong. That's the first point. The second point, perhaps even more important, was this was a $300 million program in 2011. It's about $250 million now. Guess how many PhDs were involved in it? Take a guess. Out of those 62 people, how many PhDs? Very close, 0.6. There was a lady, Marie Mapes, who was on pregnancy leave, so she was working 3 days out of the week. And so she was the only PhD in a program which was very technology focused. So the second thing we did was to change the nature of the people who were running it. By the time I'd finished up, we had 21 PhDs. And I'll tell you a quick story about how these people did active program management. And that's a story for the young people. Some of you should be thinking about serving the nation. For immigrants like myself, I felt this was the best way to serve the nation, which has been incredibly good to me. I had a PhD, a professor position at Berkeley, National Academy, blah, blah, blah. I felt I had to do something for the nation. We'll finish up with that same statement at the end of my lecture today. So it's something that you should be thinking about. You should be thinking about running for Congress. It's your country. Take ownership. If you don't take ownership, somebody else will take ownership, and you don't know what the consequences will be. Okay, so the second thing we did was to bring in top-notch technical people. This is one story. Rachel knows the story. This is one of our program managers. It was a really young lady. She had a PhD from Georgia Tech in DOE, and it turns out that we created a new format that every time we funded people at $1 million level, we would ask them to come in for an oral exam. Graduate students know what that is. It's called the qualifying exam. Except it was a reverse qualifying exam, because in this particular case, this girl's PhD advisor was on the other side. He was a very distinguished solar guy from Georgia Tech, and he was an applicant. And so I was watching, and I didn't know much about the science part of it, but I sat in on every one of these qualifying exams. And this girl proceeded to grill her advisor for 1 hour. And he's an Indian guy, and so you couldn't see him blush, but it was very clear that he was very hot under the collar. At the end of it was an hour and a half exam, and he said, Ramesh, what's going on? I said, it's your student. She's asking you technical questions. Welcome to active program management. And the intention was that when you're using taxpayer money, the taxpayer is sacrosanct. There's a poor fellow or some lady there who's sweating to give you tax money. You say, invest it for my nation. You never want to take that for granted. And I can tell you on behalf of all of us, we never took the taxpayer for granted. If anything, we put that as the highest priority for us. And the way we do it is by doing active program management, where you put a huge premium on the technical diligence, because we're working on technology projects anyway. So people were perhaps my biggest investment. By the time I finished up, Rachel and I finished essentially the same time, we had 21 PhDs in the program. And we had shrunk by about 30%. But our speed of putting out programs was 100% faster. Before we started Sunshot, it took them 15 months. Polo Ralph Lauren, fragrances from Paris came in and out of fashion. They were still putting out programs. We went from 15 months to 7 months in terms of an idea going to funded. Somebody doing research on that. That meant that we were very serious about how we did our process. So people were incredibly important. As a matter of fact, I'll finish up with some stories from LBL. We completely invest in people because that's the biggest resource. Okay, so what is this Sunshot? On the bottom, you can see the various technologies: solar, coal, nuclear, natural gas. On the y-axis, deliberately, you don't have any numbers, but circa 2010, this was about 28 cents a kilowatt hour. That's the so-called levelized cost of electricity. How many of you know what that levelized cost is? Good, that's very nice. So I didn't know, I had no clue, okay? I never looked at my electricity bill. I'm just a professor. I just went, did research, taught classes. So how many of you know what parity is? If you went to the wholesale market and said, how much do I pay for a kilowatt hour levelized cost? It's about 5 cents. If you go to the big utilities, typical value is about 5 cents a kilowatt hour. You probably buy electricity in the not the wholesale market, but the retail market at about 12 cents. California is the other end of the spectrum. We start all the way from 15 or 16 cents all the way up to 40 cents. Depending on how many Porsches you have, how many blah, 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 Teslas you have, etc. Okay, so if you look at the challenge that Steve Chu put to us, he said, solar is about 27 to 28 cents a kilowatt hour. I need you guys to bring it down to grid parity. And grid parity was 5 cents a kilowatt hour. On the 5th of January 2011, our team was just assembling. And we had a 3-hour meeting in Steve Chu's office. And by the way, I should say something about working for Steve Chu. That's one of the main reasons I went. In October of 2010, Arun Majumdar was there. He was ARPA-E director. He said, hey, can you come over to Washington? We need to chat with you. I said, yeah, okay, fine. I went there, chatted with people. I met Rachel. I said, yeah, okay, whatever. I come back the following Monday. Steve calls me. He said, Ramesh, this is Steve Chu. I said, oh my God, the energy secretary is calling. I knew Steve from my days at LBL, and so I said, yeah, okay. He said, I need you to come to Washington right away. I said, what's happening? I need you to come and run Sunshot. I said, oh, this is pretty heavy. I'd never done one such thing before, but 1, Nobel laureate. 2, Steve Chu. Steve Chu, for me, is legend. Very faulty individual, but I have not seen somebody with such deep convictions about how the world should be. It is very important to have convictions. The world has to have a certain form to it. You may be right or wrong. Only time will tell you if you're right or wrong. But it's important to have convictions. Steve has deep convictions. So when Steve said that, I had small kids. My daughters were 8 or 9 or something at that time. So I left all of that behind in California, and I was commuting back and forth for about 2 years. And it was perhaps one of the best 2 years of my life. I hate to say that this way, because one time I came back home, and I always used to talk to my daughters, my twin daughters. Oh, Rachel did that, Min Lee did that. And one of them was really unhappy with me. And she said, you seem to like your Washington friends more than you like us. Why don't you give us up for adoption? I said, oh, this is getting heavy. So I went and told Steve, look, I got to leave. I'm really happy to work here, but my family seems to be not very happy with this. But the message from Steve was, hey, I want you to look at a problem which you would think is mission impossible. That's a phone call to Tom Cruise and say, hey, look, we need some help here. How do you reduce the cost of something, make it a commodity, 5x reduction on the cost of something, make it a commodity in a 10-year period? The time horizon that he gave us to do this compression was 2020. And I'm going to show you some of the programs and what the current status is. Okay. So a 75% cost reduction in something. So the biggest thing that I want you to take away from this is the fact that energy is a commodity. If you look at the semiconductor business, microprocessors have about a 40% markup. So Intel is raking in a lot of money. People who are making DRAMs, on the other hand, have a 3% margin. There is no room for error. Energy is like that. It's a commodity, which means everybody wants to use the lowest cost process to create the energy and disseminate it. Okay? So the question is, how do you take something like solar, which is not even a boutique at that time? Only the Germans were deploying huge amounts of solar. And how do you take that and make it into a commodity? Okay? So that was the challenge for Rachel, myself, Min Lee, and the whole bunch of the team. 75% reduction in a 10-year period. Okay. So what we did was we said, okay, let's look at the entire problem. Not just a materials perspective, not a physics perspective, but let's look at the entire market. What are the things that go into making this technology? So that's shown here in this slide. It shows you that you have various components. You have the photovoltaics. Those are the panels that everybody knows. You see the pictures. Many people have it on their roofs. The other way to make solar electricity is to go from photons to thermal energy. You can go from photons to electrons, which is the photovoltaics, or you can go from photons to thermal energy, which is the big towers that you see with all the mirrors. Okay. That is called concentrated solar production. Tech to market. How do you go look at the markets? And we'll show you some reasons why. Rachel led all of that stuff. How do you look at systems integration? Because you now have a solar panel, which is part of your grid system. It's not sitting by itself. You have to understand how it fits in there. And how do you look at the other aspects of this? All the mechanical frameworks. Things we say, what research can we do? It turns out there's a lot of research you can do. But because of the fact that it's a commodity, you have to pay attention to one thing that physicists like me or material scientists, people like me, never thought about, which is the cost of doing it. And so you do all of the technology, reliability, the performance, everything, but then you have to convolute with a cost function. As a matter of fact, I had one slide which I didn't put in, is for folks like me, really at the bottom end of the food chain, all of our research looks like a very broad Gaussian function. If you can visualize a broad Gaussian, it looks like that. Once you go from research to development, the Gaussian becomes narrower. Once you go from development to the first stage of product development, that Gaussian becomes even narrower. But it's not become a delta function. Once you start to make money on that product, it becomes a delta function. So not every one of the ideas is going to make it as a product that can make money. Okay? And that, therefore, there is this immense learning process, RDDD, that you have to go through. And therefore, for us, we had to envision what are those pathways that will lead to a product that would be competitive, and then start to fund people to do that. So I'm going to show you some results effectively as of the last few months. The good news in all of this is that the cost of solar has come down dramatically, and you could see this coming down. And the target for SunShot was 5 cents a kilowatt hour, which is approximately $1 a watt. So we all used to joke that the Top Gun version of this was a $1 a watt program, the techie version. The more Sleepless in Seattle romantic version was a SunShot Initiative. And we always use the SunShot Initiative because we wanted people to hear the violins playing, so that it brought to them an ethos of how to deal with these kinds of problems. Okay, and you could see that the deployment is going up. Everything looks very positive. If you look at solar, about 40% of the recent deployment, this is data from the DOE people. It is still only 1% of the total electricity. It's not 20%. We're still dominated by fossil fuel. And if you believe in climate change and man-made effects, you have to say, hey, how do I make this 10%? How do I make it 30%? What are the things that I have to worry about to grow this? I'm going to show you some pathways and where materials absolutely are central to the game. Okay, this is just some propaganda telling you that there are 3 different kinds of markets. And the utility scale market would be the big power plants, typically a few hundred megawatt scale. The commercial is big buildings. Each building can have a megawatt of solar panels on top. And residential is what we would put on in our houses. The one mistake that we all made was thinking that much of the focus is here. Actually, it's the other way around. Much of the development, the progress has been here. And so there are some very interesting consequences. In a few minutes, we're going to say, let's go back to 1881 and question Mr. Edison. Value chain, there's huge value chain. Why am I talking about this? It's because this is creating jobs. As a president or as people in Congress, you have to worry about putting jobs. There are companies in Michigan, Dow, for example. They're all deeply involved. But it's also true that we're very rapidly losing these jobs to other nations. We're going to talk about competitiveness in just a few minutes, which is incredibly important for this nation. We have forgotten how to be competitive on an economic scale, which is, I think, very, very risky game to play. Okay, so some of the programs, Rachel remembers this slide. One of the things we said was, if you look at this, this is, I'm sure you guys know this, public university, right? Bureaucracy is everywhere, right? So you have a lot of paperwork, somebody has to justify an executive assistant, so they give you one more piece of paper, right? So you can start to multiply, each one of them costs money. So the first thing we did, and here's an example. If I want to get a permit to put solar panels in my house in Palo Alto, $300, 2 hours. You go in, fill in a form, bada bing, bada boom, right? You do it in New York City, 9 months, $3,000. And if you look at the paperwork, I have a picture which I didn't put in here. If you look at the paper trail, it looks like Intel's Pentium chip design, guaranteed. It's got so many errors going back and forth. I said, dude, how do you ever do this and get a solar panel? So the first thing we did was, hey, we need to do something to reduce the bureaucracy, reduce the red tape in this. So Rachel knows this much better because she's the one who did all of this stuff. She said, how does one take a nation? By the way, the fun part of this nation is, although it's 50 states and all this stuff, it is really made up of 18,000 plus jurisdictions. They're called AHJs. Each one of them, for example, Menlo Park and Palo Alto, literally 10 miles apart, maybe 7 miles. Totally different AHJs, and therefore they have different practices. Their permitting processes were different. And therefore, if you wanted to speed up things, make things more efficient, you needed to get it into a point where all of them were thinking similarly. So we spent quite a bit of time and resources trying to make it happen. And so we did the Rooftop Solar Challenge. And so we cut all the red tape. And we said, if I cut the red tape by 1 week, right, 600 megawatts installed, 40,000 installations, so much of reduction of red tape. So we said, hey, this is a big investment. Indeed, this was one of the most successful programs we ran. We speeded up process by simply homogenizing all of the practices. We took a page from football, of course. You have all the conferences. We said, look, let's try to make sure that these things work, like the SEC, Pac-12, et cetera, et cetera. Okay, so that was one very important component. Our friends in China helped us a lot. We were competing with the Chinese for sure, but they were also helping us because they brought the cost of manufacturing down. We're going to talk about manufacturing in the US of A in a few minutes. And I think Alan is sitting in the back. He's been deeply involved in metals manufacturing. We need to make a commitment as a nation to manufacturing. Okay? We'll get back to that in a few seconds. Another topic that we focused on was, how does a grid look like? If you remember, I mentioned question Edison. Mr. Edison, very wise, very smart guy, he set up the grid 120 years ago by using centralized generation. We didn't have solar panels in those days. We didn't have any of those. So they generated electricity in a central location, what you would call utility scale electricity. Then they had distribution networks. Okay? To put transmission networks through the nation, if you wanted to add some of them, it's trillions of dollars of investment. If, on the other hand, you said, hey, I have solar not at 5 cents, forget 5 cents, let's say it's at 2 cents. It's going to happen in the next 7 to 8 years. If it's 2 cents a kilowatt hour, natural gas is selling at about the same price structure. What can I do with that? You can say, I can go back and completely question how I disseminate and use electricity. It's exactly the same as this. I used to work in the telephony business, right? I came here about 10 years ago. My mom's she lives in India. She said, don't call me on my landline. I don't have a landline anymore. Just call me on my cell phone. I didn't have a cell phone here at that time. Why? Because countries like Asia, India, switched from old-fashioned telephony, tethered telephony with copper, to wireless telephony in a hurry. All of that was invented in Bell Labs. We invented everything in the 70s. We didn't deploy it because of a simple reason. We had about $300 billion of fiber optics and copper embedded in our network. The same thing is happening to our energy dissemination. We have a lot of transmission lines. We have a lot of utility scale generation. What is going to happen, it's happening in Africa, it's happening in India, is you're going to see a lot of local generation, what you would call microgrids. You're going to see microgrids like this where your car is part of the storage of energy. We're going to talk about energy storage in a few minutes. The houses are all sources of energy, but it's not getting energy from across the nation by 2,000 kilometers of transmission. It's locally generated. It's very much like the farmer's market idea. Okay. That's happening. It's happening because you can now have distributed solar at 3 to 5 cents a kilowatt hour. One of the big showstoppers for that is you need to be able to store energy, because solar by definition has got a time dependence to it because of climatic conditions or diurnal conditions. So that's a big issue that we need to deal with. Okay, so the grid of the future is going to look very different. And therefore, all the way from the control systems, how do I manage energy input and output at a time resolution of milliseconds or even microseconds from very different sources? How do I manage the use, efficient use, storage, and generation, all of them together? And we have programs at LBL which are dealing with this. So one of the solicitations we ran, and Rachel remembers this, we spent 9 months arguing about this. Amongst ourselves, we could not conclude what the right way was. What I wanted was, very crudely, I wanted an inflatable solar panel. I wanted a solar panel, which we call the Steve Jobs solar panel. We said, what would it look like if Steve Jobs invented a solar panel? This guy was by far one of the best systems design engineers in the world, who unfortunately has passed away. We said, how does it look like? We wanted something which is 4 times lighter than the solar panel we had it, so that anybody can go put it up. We wanted something which would communicate with the outside world. So as soon as I put the panel up, it would send a $50 check to the local authority, say, dude, I'm all set. You don't need to send anybody to do an inspection. It'll self-inspect. It'll check its temperature. It'll check all of its functioning and say, hey, I'm all good to go. All of the electronics is already available. So we wanted a panel which would be a plug-and-play panel. And this is happening already at the early stages. People are already, if you go to Home Depot, they give you some plug-and-play. But it's going to get very sophisticated. And the analogy I give is like televisions. If you look at early days of television, 1950s, 40s, people used to have permits to get TVs. They still have it in parts of the world. India had it for a long time. The English have it. Parts of the US has it too. Then they figured out it's not worth it. Let's just give it to everybody. Let's make the money on advertisements. So how about making the solar panel very user-friendly? What kind of intelligence do you need? So that was this solicitation, which unfortunately we ourselves could not agree on. It took us a while. Actually, somebody figured out. We funded people. We spent about $20 million. We funded, and somebody came up with a really good concept. The other thing we did is to do startup companies. And that's where the innovation of this nation is at the best. Right? This slide tells you a lot of information. I will summarize it for you. What we did was we said, look, we can do technical diligence very well, which means if a small startup company wanted to build a business, they could come to us and we'll look like a venture capitalist. Except we did very intense technical diligence. We would rake them through the coals and stuff. 3% of the people who applied got funded. But here's the interesting news. once they went through the DOE process, outside people, venture capitalists said, oh, you've gone through Sunshot, you should be good, we'll give you money. So the leverage of your taxpayer money was 20 to 1, approximately 22 to 1. So you can see the numbers. We invested about $160 million. It's turned into $3.4 billion of post-investment, not co-investment, but post-investment. Why? Because of the technical diligence that we talked about. People were doing very careful diligence of the ideas that you're presenting. So it led to a lot of startup companies, especially in the financing area, where all of the new models that people use now were all started with Sunshot. Okay, now of course we haven't talked about materials, which is pretty strange, given my background. So one of the things we were pushing for, you see in the slide that many of the new materials, including stuff that you all are working on, were either funded by DOE. You can see 50% of all efficiency records were funded by the Department of Energy. More than 30% of the patents in solar are linked to IP that's coming from DOE. But I wanted this is one solicitation where I worked a lot myself. I worked on all of them, but some of them I wasn't really the expert. I listened to other people. This one was something that we call the Michael Jordan solicitation. Right? I'm sure you guys have seen Jordan, right? Nobody's not seen Michael Jordan. If you want to mess with Michael Jordan, you really have to play basketball like Michael Jordan. That's the only way you can do it. You need to have Air Jordans and you need to be able to score points, right? So we said, if you want to mess with silicon, 90% of the solar market is silicon. If you want to mess with silicon, you have to be like silicon. And that is really the fundamental material science issue. The reason silicon is so important is very simple. The fundamental science system that Marvin Cohen, my colleague in the physics department, did the ab initio calculations in 1984-85 is exactly the same system that you put on your rooftop. No difference. Single crystal of silicon. Actually, if you use polycrystalline or amorphous silicon, it behaves totally differently. It's not as good. And therefore, the single crystal from science is the same single crystal from technology. And therefore, you didn't have to worry. You look at First Solar's CAD-TEL, it is no relation to cadmium telluride, which is the material that you study in your classes. SIGs, copper, indium, gallium sulfide, same. The material that you make is not the same that you study in the class. So we launched a solicitation, which actually was very successful, where he said, how do you make CAD-TEL or SIGs, which has the same theoretical efficiency of about 30%, 29, 30%, but where people are making cells at 12 to 13%. We said, how do you make it at 28, 29%? What is it that you need to do? And the hypothesis was that I need to make a single crystal of this material. And that's where material science, physics, chemistry, chemical engineering, all of them were very valuable. And that was about a $25 million program we ran, which was very successful. Efficiencies have gone up quite a bit for these other materials, and they're getting closer to silicon. Why is that important? The entire silicon market is now in China. All of it was invented in this country, but not being manufactured in this country. We'll talk about manufacturing in just a second. Okay, this is circa 2 weeks ago. Sunshot goals, we had 10 years time, Steve said. We were already, and it was very clear to me at least. I was very aggressive. I wanted to be aggressive. And I was pushing Steve to go to 3 cents. And Steve was getting feedback from the industry guys saying, Ramesh is inhaling stuff in California. Absolutely don't do it. They were pushing him to go to 8 or 9 cents. And I was saying, no, a government program should be pushing the people to reach for things. You may not reach it, but if you do, you'll make a big difference. So we've already reached Sunshot targets. That's what this data is saying. So our 2030 goals, we just recalibrated. I shouldn't say ours, I'm not involved anymore, but I have a huge parental ownership on this. Is how does one shrink it further? How do I go from 5 cents to 3 cents? And further, how do I put storage into it? And you can say, hey, what's the deal with storage? And the deal with storage is, if it's like today, you have clouds passing by, the output of your solar panel can change sometimes by 60% on a time-resolved basis. So it looks very much like an optical spectrum. So you say, how do I flatten it? How do I do a flatliner for solar? And here's an example where energy storage is really important. And this data just shook me up. This is real data, right? from California, where there's lot of solar electricity. In local parts of California, you can have 70% of the rooftops covered with solar panels. Okay. This is a particular day. It's the 11th or 12th or 11th of March this year. What I want you to notice is the plot at the bottom. This is the cost per megawatt hour. This is the selling price of electricity. Look at this. It's negative. What it's telling you is that there was so much of solar electricity being produced that the trading price of electricity was negative. You say, wow, that's strange. It's completely changed the market dynamics. So what can you do? This is a fantastic example of storing it. You can say, how do I store it? I can put a battery, and we're going to talk a little bit about it. That innovation has not happened yet. For the students in the audience, or the professors too, that's a huge topic. If there's one topic you want to get into, is energy storage. Or you could convert it into other value products. You can desalinate water. We're going to talk about water in a second too. So this is what an output looks like. This is a real plant in Nevada. 20 megawatt plant, and it looks exactly like an optical spectrum. You could do Fourier transform and do all the analysis for that. What you want is a flatliner. The grid gives you a thermodynamic equilibrium. It gives you a flat line. Well, you have something like this. So storage is by far the final frontier for these technologies. Once you have storage at a cost structure that's affordable, the game is going to be fantastically different. Whoever discovers this, forget about the Nobel Prize. You will be giving out Nobel Prizes. You'll be so obnoxiously rich that you will be giving money to other people. Now, I mean it seriously. Why do you think Tesla is building these factories? It's because it is really the final frontier. We now understand how to bring the cost of solar down to very low levels. Wind, same story. Then you say, we'll spend a minute, material science. I haven't talked a bit about material science. There are some fantastic opportunities to innovate. If you look at how we store electricity, it's got to be, it's very draconian. You say, dude, why am I doing this? We take photons, we convert it into electricity through a solar panel, for example, and it goes to somewhere where it converts it back into some electrochemical energy, and you store it, and you retrieve it back, so on and so forth. Why am I not directly taking photons and converting it into a stored energy? And so this is an example from one of my colleagues. These are fulvalene compounds, ruthenium-based compounds, which undergo isomerization transformation. People have studied it quite a bit, right? That transition is accompanied by an energy of about 1.3 EV per mole. So about 30 kilocalories per mole. So you can capture it and leave it there. Then you come back and catalyze it, and you release that energy. Okay. So one needs to start thinking about energy storage in ways that we have not been taught. We're always taught it's got to be lead-acid batteries or lithium-ion batteries, etc. We'll talk about lithium-ion batteries in just one second. But one really needs, from the material science perspective, fundamental chemistry, physics perspective, how does one understand interaction with photons with chemical species, and how do you store that energy? And then retrieve it at some other point. So clearly you could see this fundamental science that needs to be done. At LBL, we are deep into asking another question. If you look at the evolution cycle for lithium-ion batteries, typically most hardware technologies, for batteries from genesis to production and commercialization, 18 to 20 years. Okay? And you say, how does one speed it up? Is there a pathway? That's not a fundamental time constant. How does one speed up the generation of these kinds of technologies? So we have a program which says, how do I use things like machine learning, or rapid prototyping, 3D printing? That's very popular here. Jyoti Majumdar is doing quite a bit of that work. How do you use those kinds of ideas to speed up the discovery to translation process by 5x? Instead of doing it for 20 years, can I do it in 4 years? So we're pushing very hard with those kinds of ideas, because 4 years really means you can go through many more cycles of learning. But global competition is fierce. Okay? About a month ago, the Chinese announced that they're building factories which are X times bigger. X is large number. than Tesla's, not less than 1. X is about 5 to 7 times larger than Tesla's Gigafactory in Nevada. Okay? And so I want to tell you a story, and this slide comes from when a bunch of us, a few of us were helping Steve Chu with his Senate testimony on Solyndra. A lot of people talk about this and that. I don't think many people in this nation know the background behind Solyndra. Okay. I want to tell you the story. The reason I want to tell you the story is it tells you how market forces drive things. Okay. So what is this data looking? This is actual data. Okay. This is data. The blue bars are basically the price of silicon, silicon panels. And the green bar is the raw material price. Okay? So let's take the raw material price here, price per kilogram. If you look at first quarter 2008, price of silicon was $450 a kilogram. People like MEMC were making obnoxious amount of money. They were not spending that much to make the silicon. It was because everybody was saying, oh my God, we're going to make a killing because the Germans were deploying a lot of solar. Okay. Today it's about $18, about 25x reduction in the price of silicon. Okay. So the actual cost of the Siemens process, it only costs about $6 to $8. So it was huge amounts of flexibility. Okay. That's one point. And the corresponding change in the price of the panels, actually this has dropped quite a bit. But that was not the only thing that was happening. If you look at this data, and I'm going to be a little bit critical about some things. If you look at this data, you can see these curves. Each one of these are market predictions by all of these people. UBS Securities, Barclays, BNEF, everybody. Every one of them was doing linear analysis and saying, oh, you know what, the price of solar panels is going to decrease by 8 to 10%. If you do very simple linear analysis, that's what you would get. Okay? On the other hand, what was happening in the solar market, and I remember this day because this was the first week of November, and Steve's testimony was on the 16th of November. It was a Saturday morning when we were going through this data. We said, oh, this was one of those eureka moments. The eureka moment was the following, that if you look at the solar market, at that time, literally all of the solar deployment was happening in Germany. And for those of you who follow the German market, I learned how to follow it, they used something called the feed-in tariff. What they did was, in the late 1990s, 1999 timeframe, they went and told people, hey, look, if you put solar panels in your house, we will buy your electricity at 54 cents a kilowatt hour for 20 years. So people who were doing pig farming in middle Germany killed all the pigs, ate it overnight, converted it into solar panels. They were making huge amounts of money on it. The government figured out, dude, I can't do this forever. So every 18 to 24 months, they were dialing down the market. And you could see that the things would spike. As soon as the German market dialed down, things would spike down as well. That data I have as well. So the Germans had done one such dial down. It was going down from about 38 cents to about 28 cents, something like that. Okay. But everything was following the German deployment market. So right around this time, Solyndra was coming and saying, hey, we have a brand new technology. We don't use flat plates, we use cylinders. Okay? Nobody ever bothered to ask, what is the thermodynamics of a curved surface? Okay? There was no materials person involved because DOE was funding it based on a financial model. First mistake, right? Typically when you have these new technologies, you do 3 kinds of diligences. You do a technology diligence, which is this technology a robust technology? Especially when you're competing in a commodity market, your technology has to be very robust. In semiconductor language, that robustness is measured by one parameter. Does anybody know that parameter? It's called yield. If you go to Intel, there are only 2 things that all of the people will talk about: yield and reliability. Yield tells you how many of the wafers you can sell and make money. Reliability says how happy your customer is going to be. Okay. If you look at silicon solar panel yield, it's about 97%. Trina, all of Suntech, everybody, SunPower, a US company, all of them were making solar panels with 97% yield, which means almost all of the wafers they were making, they were selling. Solyndra was 49%. So, but the DOE people did not do the diligence on asking, dude, is this technology robust? And it's not going to be, because you took a flat plate, that took 30 years to develop, and you made it into a cylinder. And nobody asked the question, hey, what happens on a curved surface? You have thermal stresses that are very bad. You can have cracking. And the material they were using, which is SIGs, was very susceptible to corrosion. As soon as you have cracks on the sealants, you start to have water getting into it. And so they had to, so the joke was that if you went to Fremont and you went behind Cylindra's fab, you see big crates full of useless panels. Okay? And therefore, it's completely a materials problem which they overlooked. The second part of the diligence has to be a market diligence, which Solyndra was okay. The market diligence says, look, how does your product fit into the global market? Right? Are you selling at the right price? Do you have a competitive advantage? They were actually 15% lower in price compared to silicon panels. The only problem was they were only yielding at 50%. Okay? And therefore, what happened with the diligence was they did the financial diligence and they said, yeah, everything is fine. They never looked at the technology part of it, which was pretty goofy. Okay? So Solyndra, we argued, was caught in a perfect storm. And the perfect storm has three parts to it. The first part was the fact that right around this time, the Germans were dialing down their tariff, which means they're reducing the consumption of solar panels. Everybody, including us and the Chinese, were saying, oh my God, the Germans are going to be deploying a lot of solar. We got to build more panels. So Steve was telling us a story that if you flew over Beijing, you could see smokestacks coming up producing silicon by the Siemens process. Right? So there was a huge oversupply of polysilicon, approximately 2-to-1 oversupply. Okay? Then you had the feed-in tariff. The third part of it has to do with government policies. And again, there's a huge lesson to be learned. The Chinese were providing about a 30% advantage to their producers by giving in policies. The story was, and a lot of people have done this, you go to Beijing at that time, 2008, 9, 10 time frame, you had an idea, you get $20 million. Your employees got free food. They built a dorm for you. They gave you 20 years water and electricity. And you add all of them up, they add up to a 30% advantage, which we didn't have. And so we thought they were violating WTO practices. The Chinese said, no, we're not. It's our nation's policy. We can do what we want. There was a lot of back and forth on this. But the three of them together meant that you could not do linear analysis anymore. You now have three forces. It's very much like a magnetic transition. This is the M versus T for a ferromagnet. You cannot get a ferromagnetic state by doing a linear extrapolation of your free energy density functional. You have to have forces. In our case, it's exchange forces versus thermal forces. And those are very nonlinear. Those are emergent phenomena. So what had happened in the solar business was an emergent phenomena where multiple forces came together at the same time. It completely changed the market dynamics. It meant people like Solyndra went out of business. The solar market is dramatically different today than it was in 2008. So for us, it was a big learning. We actually started to do the science of emergent phenomena. My own research is electronic emergent phenomena. I put electrons in some systems. They start acting like human beings. And so how do you start to simulate that on a global basis? There are lots of interesting problems to focus on. Okay, I want to finish up with a few remarks on what we're doing. I learned all of this. I had totally no clue about this. Working with folks like Rachel and the entire team was perhaps the best thing that happened to me. I learned all of this and I said, hey, I need to do something about it. The biggest learning for me was that as a science person was that you can do fantastic science, but if you want to translate from science to a value proposition, which is not a science paper or a Nobel Prize even, but you want to impact humanity, then you have to pay attention to some things. In a commodity market, you have to convolute all of them with cost as a variable. Actually, that's the ultimate convolution. So we said, okay, these are the four components of the energy landscape. And so they asked me to go back to LBL. I'm the Associate Lab Director for Energy Technologies. So we launched our area. We have 6 initiatives, and I'm just going to quickly go through a few of them. So the first one says they all have the same ethos as SunShot. They have a target, they have a time constant. For all of our initiatives, they have approximately 2030. Good number, 10, 15 years kind of time constant. The first one says, how do I reduce energy consumption in buildings by 50%? Why is that important? If you have any hope of solving the climate change, and if you believe in it, first of all, then 38% of primary energy in this nation is in buildings, heating and cooling. Michigan is a good example. Not very easy to solve the problem. Can anybody answer the question why? Why is it that you cannot turn a knob like we do in our PLD systems and solve the building's energy problem? There's a very simple answer, actually. Cost, of course, is true. As a matter of fact, you're plumb on. There's another more simpler. It's the fact that 80% of the buildings are already built. Retrofitting is a very tough proposition. If you go to an apartment complex in Michigan, anywhere, in New York, and tell them, hey, look, you should be doing energy retrofits, the first question they'll ask is, hey, what's in it for me? So we are pushing a program which says, hey, how do I monetize energy efficiency? Nobody has done that, which really means you have to do the science behind energy efficiency. And therein lies a very interesting observation. If you look at it, nobody understands how the energy consumption of a building is going to look like a year after it was built. You will see things like, oh, it's LEED Platinum certified. Very nice. But nobody measures it after the fact. A building is spec'd out for 20 to 30 years, but nobody measures it after that period. And therefore, you have no clue whether it's consuming more energy, less energy. We said we can solve that. So we are setting up systems level examples where we can measure things, model things, and then predict what the energy consumption is going to look like. That's our buildings program. Our transportation is the moving analog, which says, how do I reduce CO2 emissions in transportation by 50%? One way is to completely ditch internal combustion engines. The mechanical engineers, if there are any, they'll probably shoot me. But China is already doing it. California just came out 2 days ago. A year ago, we were BSing with our folks in Sacramento saying, wouldn't it be nice if you ditched all ICEs and put batteries instead? And they actually came out with a statement. The governor's office is trying to push this notion of how does the world look like if I have no internal combustion engines? I say that's a purely materials problem because today's batteries are neither reliable enough, they don't have the range enough, nor do they have the cost structure. And therefore, for folks in this room, you should be saying, hey, look, I need to work on solving this problem. Lithium-ion batteries are about $300 a kilowatt hour. For it to make sense, it needs to get down to about $50 to $70. Again, the 5x number. Okay? So how does one go about doing that? That's a big portion of our grid initiative is just a takeoff on solar. It says if I have 50% of solar or more in a distributed fashion, that grid is going to look different. Again, storage plays a big role. Okay? Let me skip these two guys. This has to do with manufacturing and stuff, and focus on this. You guys know how big a problem it is. One word for this, Flint. Water is a very fundamental problem. I grew up in India having to wake up. My sister and I used to have vicious battles. We were 2 years apart. Who would get up at 3 o'clock to catch the water? Potable water would come for an hour from the government. Okay. In this nation, we have never, until examples like what happened in Flint, Michigan, right? We have never experienced the negative side of water. You go to Bangladesh, arsenic in the water. You go to the Bay Area, Santa Rosa has arsenic, and the wines have arsenic in them. So potable water at a cost structure that's affordable is a huge challenge. Therefore, we have a water initiative which says, how do I reduce the cost of making water? For people who live on Sierra water, it's free. But if you look at how water is supplied in California, we pump it down to San Diego and LA. That raises the cost from about $400 an acre foot of some volume to about $2,000, 5x again. How do you reduce the cost of desalination? At core, it's a materials problem. How do I create membrane technologies that can separate chemical species? How does one overcome entropy of mixing? The entropy is a nasty problem to deal with, as we know, but how does one overcome with the lowest penalty on the cost of doing it? That is going to have huge global impact. I'm convinced that the next big conflagration is going to be based on water. Energy is all done, not fashionable anymore. Okay, so I I will talk a little bit about this, and I want to skip a few slides because we've spoken enough. Again, my favorite president. This is amazing, the statements he has made. This is 1962. You just have to read this and say, wow, this is 60 years, almost 60 years, 55 years ago. You can read it. And so it's a very fundamental problem. Until you really live that, it is very difficult to, you see what's happening in Puerto Rico, for example. Potable water we take for granted. We should not. Another topic we're working on is the fact, one of the guys from RPE joined us, Ravi Prasher, really big expert on thermal energy management. So we're looking at the full range of thermal, chemical, electrical, mechanical energy conversion back and forth. So I'll just show you one slide on what we're doing. If you look at the energy landscape, we use about 100 quadrillion BTUs. Approximately 10 to the 20th joules per year is the energy consumption of the US. The quadrillion BTUs is the Brit units, okay? We only use 39 in real form. We throw out 60% of the energy as waste heat. And therefore, if there's another thing that you would do, we've talked about energy storage, we talked about water. If there's another materials innovation that you would follow, is how does one convert that waste heat, different qualities of waste heat. The automobile exhaust is at 650 C. There may be other environments, steel plants, 800 C. There may be others which are at 100, 150 C. How do you convert that? So we are putting together a very large game plan, which we call HEATER, highly efficient advanced thermal energy research, which is how do I look at the fundamentals of thermal transport. So let me just, that's a material slide which we should talk about. People have not paid attention. Since the first Nobel Prize, there's probably about 20 Nobel Prizes, maybe more, on electrons. There's only one I can think of for Nobel Prize on phonons, which is the BCS, Barton Cooper and Schrieffer, for phonon-mediated superconductivity. But the question is, if phonons are that important, thermal transport is that important, how come we're not paying attention to the limits of thermal conduction? This is data. The highest is about 2 kilowatts per meter squared per Kelvin, but theoretical limits are 6 orders higher. So there's huge space to innovate. People should be going gangbusters, making new materials, looking at new heterostructures, new composites. On the low side, how do I completely suppress phonon transport? How do I make a super thermal insulator? Again, it's a great challenge. We know how to make an insulator and a superconductor. How come we don't do it for thermal transport? Huge impact. Similarly, heat transfer. What are the limits? We're so far away, in this case about an order of magnitude away. Thermal energy storage. So somebody who was talking about CSP. Now, the limit is gasoline, right? That's our gold benchmark, 40 megajoules per kilogram. We're nowhere close to that. That's why everybody wants to use gasoline, because it's got very high energy density. The energy value in gasoline is very high. Then, of course, conversion of heat to electricity, we're still at 15 to 20% of Carnot. So there's a large amount of headroom to innovate. And I argue that all of it is in materials. So we should all be finishing up after this lecture, go to the lab. By the way, this is a big problem at Berkeley, and I need to talk about this. I cannot tell my postdocs work after 5 o'clock because the union will come after me. I said, dude, I've never seen 5 o'clock in my life. I typically go home. John, when did you go home?
After you did.
Oh, okay, fine, yeah. Right. That's right, yeah. Yeah, we're all hackers, right? Who cares about 5 o'clock? We just want to, science is fun. But I'm worried. How can science become in that domain? I don't understand this. Okay, then the last piece of it is going to be a precursor for tomorrow. If you do come after all of this stuff, if you say, oh, I got to come to the technical lecture, what we're going to talk about is another issue which is becoming more and more important, which is this notion of microelectronics. Today, we use about 4% of our total energy for microelectronics, so nobody pays attention. But there's a revolution that is happening called IoT, Internet of Things. Basically, for folks like me, I understand that every one of your system, macro system, whether it's a hospital, a highway system, a manufacturing environment, or whatever control systems you have, everything is going to be automated. And therefore, at core, there's a silicon chip somewhere which is consuming power. And so the standard rule of thumb in semiconductor electronics is that market is about $300 billion. Not true anymore. People suspect that that market will become about 20 times larger because of all of these components putting in. And so this is a chart which comes from this agency. There's a lot of debate going on about this. If you believe all of these, it means that by 2030, if nothing happens to semiconductor electronics, about 25% of primary energy, which is how much of coal you burn, will be required to keep all of your electronic systems, the Googles of the world, all the data storage centers, everything running. So it's not a trivial number anymore. Okay. On the other side, Moore's law is pooping out because your transistors have already gone down to 7 nanometers. The power loss in transistor circuits is going up significantly. And if you just touch your Pentium, it's probably putting out 400 to 1,000 watts of heat. So if you do nothing and they're operating at about 100 picojoules per operation, you're about 20 to 25% of primary energy. And therefore, we're saying, hey, here's an opportunity for folks in the physics, electronic materials area to innovate. The question is, how do we go about innovating? Can you go from metal lines to optical communication? If you look at the total energy consumption, significant amount is wires. I squared R, joule heating is a big problem. How does one deal with that? Can we go to optics? That's one pathway. I myself, John started this when he was with us. He wrote a fantastic paper, which you'll hear about in great detail tomorrow, in Nature, which talked about electrically controlling magnetism, spins of electrons. And so we think we can go down by 6 orders of magnitude in energy consumption per operation by that process. Intel is very interested in this. So this is a topic which we'll pick up tomorrow. I'm just wanting to give you a nexus for tomorrow. So we want to do something where you're significantly reducing that. You could do it at a systems level. You can do it at the algorithm level. You can do it at the chip level. You could do it at the device level by focusing on various things. So we'll talk about that tomorrow. Again, this is a global You've heard me say this a couple of times now. We as a nation need to be savvy to global competitiveness. I'm going to finish with this example. In 2012, the US government told Intel that thou shalt not sell microprocessors to China. Okay? Because the Chinese were building up, and I think there was concern that they're going to use these for simulating codes and stuff like that. I said, fine. So they invested $150 billion, and they built semiconductor fabs in Wuxi. A whole bunch of design engineers came together. They built this computer, the Sunway Taihu Lite, and last June they made the announcement, which shook everybody. Everybody said, dude, what happened here? It was the fastest computer, the most energy efficient, about 25% more efficient than the Oak Ridge machine. The Oak Ridge supercomputer is the fastest in the US, Titan. So this one, all of a sudden, became the fastest in the world. And so we had 2 problems at that time. First, now they could make these parts and sell it worldwide, which means if the market is 20 times larger, Intel is no more the biggest gorilla. There are other gorillas doing this. That's the first problem. And the second problem was that they now had the top 2 computers in the world in China. Okay. And therefore, this is a global competitiveness. Clearly, if you believe in climate change, there's energy consumption, therefore you're burning more fossil fuels, there's a market share issue, and for us, there is a national security issue. We should not overlook that. So energy, security are always intertwined. They cannot be separated. Okay. So for everybody, this notion of making things in the nation, that's why with Steve we used to say, invented in the US, made in the US, sold worldwide. We should be doing it. Right? We have gone away from that game plan. And that is a big question. For old fogies like me, maybe we're popping off, doesn't matter. For my kids' generation, for all the young people in this audience, you need to say, hey, what's the universe that we want? This is by far one of the best places in the world to live in. But we need to be competitive. Ask yourself, are we being competitive? So, in closing remarks, I will go back to Mr. Kennedy again.
In the long history of the world, only a few generations have been granted the role of defending freedom in its hour of maximum danger. I do not shrink from this responsibility. I welcome it. I do not believe that any of us would exchange places with any other people or any other generation. The energy, the faith, the devotion which we bring to this endeavor will light our country and all who serve it. And the glow from that fire can truly light the world. And so, my fellow Americans, ask not what your country can do for you, ask what you can do for your country. My fellow citizens of the world, ask not what America will do for you, but what together we can do for the freedom of man.
Never been more appropriate for this nation. I've heard this a few thousand times. Every time I hear, I have tears in my eyes, because this is, to me, very important. It is perhaps the embodiment of what we should be thinking. Thank you so much. Of course, questions.